Hello, my friends. Welcome. Today, I want to talk about some polynomials. Polynomials. Higher degrees than just maybe x squareds or x to the first or things like that. So get something to write with because we're going to be doing some thinking. Thinking means connecting things, and we want to have a record of it. And so let's go ahead and get started. Okay, polynomials. Books usually give like a very lawyer type definition of what a polynomial is, and you're going to see this a lot. So let me translate for you. I'll translate it over into regular kind of speech. But before I do that, let me share a joke with you. What do you call a polynomial? What is a polynomial? It is a parrot with nothing to eat. Poly, no meal. But that's just the joke. All right, so the book's definition would be of a polynomial would be a function in the form of like f of x is equal to, and follow along with me here. It would be a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 plus dot 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 a middle somewhere plus a sub 2x squared plus a sub 1 x plus a sub 0. And you're going to say, holy smokes, what is all of that craziness? Well, mathematicians like to say some things generally without being specific. And so this a sub n and n minus 1 and then so forth and so forth on is just a way of saying the important things without actually saying what the important things are. Even that didn't even make much sense to me. Let me give you an example. How about I do f of x is equal to 3x to the 5th minus 4x to the 4th plus x cubed minus 6x plus 12. And now let me just ask some important questions. What is a sub 4? Now, what I want to point out is this. You probably noticed this, but if you didn't, let me point it out to you. This little n right here, did you notice that it was kind of matched with this n right here? And the next one was an n minus 1. Did you notice that this one was an n minus 1? This one's an n minus 2. That one's an n minus 2. This one's a 2. That one's a 2. This one's a 1. This one's a 1. This is a nothing. What are the little n subscripts for? All they are is they're a matching between the exponent on x and the number out front that's matched with it. So when I say a sub 4 down here, all it is a little name badge, and it means I'm the number that goes with x to the 4th. What is the number that goes with x to the 4th? Negative 4. Do you see that? Find x. This is 4. Find x to the 4th. Find the number on it. Find the coefficient on x to the 4th. So a sub 4 is negative 4. It's just a way to pair up and to tell me which coefficient that you're talking about. this a sub n and this a sub n minus 1, those are just the coefficients on those x terms. That's all they are. And the little subscript there is a way to connect which one you're talking about. So what if I said a sub 5? It's asking what's the coefficient on x to the 5th. Can you find x to the 5th? Oh, here it is. What's the coefficient? 3. You get it? What is a sub 3? It should be 1. Let me give you one that'll give you a headache. How about a sub 2? What's the coefficient on x squared? Well, there isn't one. Well, there kind of is. You don't see it written there because it's got a kind of a unique number that's being multiplied by it. What number do you multiply x squared by to like cancel it out so it doesn't show up? 0. Do you agree that maybe kind of tucked in here we might have something like a plus 0x squared right in there? Yeah, it's like a place value thing. Did you notice that all of these exponents are counting down? That's another thing. Okay. Did you notice it goes 5 and then 4 and then 3 and then like an unwritten 2 and then a 1 because the exponent here is 1 and then x to the 0, right? Did you notice that that pattern is what shows up over here with the general form? N is where it starts. 1 minus n, or 1 subtracted from n, and then count down by 2, and then count down by, we don't know how many. Because see, the reason that that's n right there and not a number is we don't know how high it goes. Well, on the second one here, I knew it went up to 5, so it counts down. 5 minus 1, 5 minus 2, 5 minus 3, and so forth and so on. That's why this one counts down n minus 1, n minus 2. We're just subtracting 1 and counting down. And we've got to have a place for each one. Now, we don't know how high it goes, but eventually we get down to squared, x to the first, and then so forth and so on. So a polynomial is just a function that has as its exponents what you and I would call positive whole numbers, positive integers. 5, 4, 3, a 2, nope, that wasn't with a 2. The 2 was missing. A 1. Oh my goodness, that was highlight. I'm having a hard time here. I can manage. Watch me. I want to erase the 2. I want to do a 1. There was the 2. And then it's 1. And then this one's x to the 0. Okay. So no negative exponents. No fractional exponents. No two variables multiplied by each other. You're not going to see like an x and a y or something like that. So that's the definition of a polynomial. And we get into what are called power functions. So let's talk about some power functions here. Let me do one like this. If I said something where it was y is somehow something x cubed, it would be a graph. Notice I didn't say equal to, but it would be a graph that might look like this. And I'm going to use this one kind of as my general template for this. And then on the other side, on this one, let me do something like another power function. Y is equal to, not equal to, because I don't know exactly, but it's related to x to the 4th. Doesn't look like an x, that looks like an alpha. And that one would maybe look like this. Okay. I've hinted at it in previous videos. I can't actually do it at this moment, but I want to point out something to you, and that is, do you see this exponent here? Yes, it's 3. How many times does this graph here then cross the x-axis? 1, 2, 3. What's the exponent here? 4. How many times does this one cross? 1, 2, 3, 4. There's a connection there. And it's fundamental. keyword. But I can't get into it right now. The fundamental theorem of algebra is something that doesn't happen at the beginning like maybe you would think it would be. It kind of happens close to the end. Because sometimes what's basic is not obvious. And a lot of times we need to teach with the obvious first, and then we get to basics. For example, biology. What's the most basic thing in biology? The cell. But that's not what obvious. When I look at people, I don't see cells. I see like arms and legs and heads and torsos and stuff like that. When I look at plants, I don't see cells. I see trunks and roots and leaves and flowers and fruit and stuff like that. So sometimes the basic things have to be saved until later. And it's best when you learn it that way. Teaching a second grader set theory in mathematics is probably not a good idea. But we should start with something obvious like 5 plus 7 is 12. That's good. But it's not basic. But it is obvious. Anyway, so before I jump back into these, let me make a final point here. When you have a polynomial that is in proper form is going to be when it is in descending degree. The degree has to do with the exponent, the degree. This one that I gave right here, that's a 5th degree polynomial. The highest exponent is a degree. And when you write it in order of descending exponent, like you should, that's standard form, the coefficient that's out in front is called the leading coefficient. So the leading coefficient is the coefficient that is on the variable with the highest degree. And the degree and the leading coefficient now are going to give us some important properties about the graph of the function. The degree of this function is 5, which means it's an odd degree. Odd degree functions look like this one right here. I've got something cubed. Notice the end behavior. The end behavior of an odd degree function rises on one end and then sinks on the other end, and it does something sometimes in the middle. Even degrees like this x to the 4th always point in the same direction, either both up or, as we've seen with parabolas, both down. When we did parabolas, didn't we have parabolas that went both sides up? Yes. Didn't we have parabolas that went with both sides down? Yes. This one was something like y is equal to negative x squared even exponent. This one was something like y is equal to positive x squared. So the leading coefficient, the number that's out in front, tells you something. For an even degree one, if it's positive, they both point in the same direction. The end both points in the same direction. So if your a is positive, for an even degree, both ends point up. It opens up. If a is negative, maybe I should put the sign in front. I should put the sign in front. That's normally how you write it. Negative a. For an even, it opens down. Okay? That's the end behavior of an even one. Now, an odd one is a little challenging, which is why I did the even one first. If the a is positive, positive a for an odd degree one, positive a does this. It's kind of hard to write with symbols or something like this. It rises to the right and falls to the left. And then for a negative a1, it does the opposite. It rises to the left and then falls to the right. You kind of can do like a dance with this. Like if it's an odd degree positive, it's going to go whoop. And if it's an odd degree negative, it goes whoop, like this. And then if it's an even degree positive, it's and then if it's an even degree negative, it's and then the middle does something and they're like that. So, you know, the polynomial, something like that. What does mathematics have to do with dance? More than you know, probably. More than you know. But we got to figure out a better way to say this. Let's do this. Let's talk about what we're doing x and right, or x for left and right, and then we'll decide what we're going to do up and down. So end behavior for an odd one. If the a is positive, as x goes to the right forever. How do I want to say mathematically goes to the right forever? I will use this. As x goes to positive infinity, because that's going to the right forever. The little arrow means as it goes towards that thing. As x goes to the right forever, what happens to the y value, f of x? Well, what did our graph of x something something cubed go? It goes up forever. How do I write up forever with an f of x? Also positive infinity. But you have to realize here that x only goes left and right. So when I say x goes to positive infinity, it means goes to the right forever, because to the right is positive on the x. Okay? This means the y value. What direction does the y value go to if it goes positively? It goes up. How far? Forever. Okay. I've got something else now. X can go to the right forever, but x can also go to the left forever. How do I write forever left? It means going this direction. What sign, positive or negative, means to go to the left on an x? Well, that would be a negative. And I want to go to the left forever. So now this is to the left forever. What did our y value do on this graph as we went to the left forever? See, look, here I am starting kind of in the middle, and I'm going left now forever. What does the y value do? It goes down forever. So the follow-up statement would be f of x, the y value, goes down forever. So that's the end behavior for a positive a. And let me say it again, kind of starting in the middle. As I go to the right forever, what do I do on the y? I go up forever. It goes up forever and ever and ever and ever. Now, starting in the middle maybe, and then going to the left. What do I do to the left? I go down forever, forever and ever and ever. So that's end behavior for x cubed. What about if it's got a negative a? What if I said something about y, that's supposed to be a y. One of these days I'll get to do geometry and use these cool features of switching. Y somehow related to negative x cubed. Well, it would switch. So the graph would look something, let me do it in green here. The graph would look something like this. It goes from like this to that. All right, so how do I write that? So as x goes to the right forever, what does the y value do? F of y, look at me, I'm a bozo. F of x. What does the y value do now? So as I go to somewhere in the middle, and as I go to the right on the graph, what does the y value do? It goes down forever. How do I write that? F of x approaches negative infinity, goes down forever. And then as x goes to the left forever, f of x then goes to positive infinity. And hopefully you can see that then by the graph. Starting in the middle and going to the left, eventually I go up, right? This is not middle behavior, remember. This is end behavior. After it starts going up and down and then picks one thing and goes like never changes, what does it do? Whew. How about end behavior for an even function or an even degree function? Okay, let's talk about that. For a positive a, leading coefficient that's positive, as x goes to the right forever, what does f of x do? F of x goes to, starting in the middle and going to the end. I'm going to the right forever. What does my y value do? y value also goes to positive infinity. And as x goes to the left forever, what does the y value do? Well, starting in the middle and then going to the point where it doesn't change and it goes one direction for the rest of the trip, that would also be going up forever. So notice this one's positive infinity as well. Okay, they both go the same direction. What do you think happens for a negative a? What about y is somehow related to negative x to the fourth? What does the graph of that one look like? Hopefully you're savvy enough now to do something like this, where it would go like that. Here, let me erase some of that clutter right there. Okay. Now, if negative a, what happens here? Well, as x goes to the right forever, f of x, the y value, does what? Well, start in the middle, find the place where it goes one direction, doesn't stop. What does it do? It goes down. How do you write down? It goes to negative infinity. The y values go to negative infinity. And then as x goes to negative infinity, what does the f of x do? The same thing on the left-hand side. If you start in the middle and then find where it starts going one direction and doesn't ever change, it goes down forever. So that's the mathematical way of saying all of those things about end behavior. Pretty good, eh? Yes. Let me look at my notes here, make sure I'm not forgetting anything. We did even and odd degree. We did end behavior. Yeah, okay. Now let's talk about let's talk about zeros. Yeah, that's the next thing over here on my list. Real zeros and extrema. All right, so maybe I should have put this title down below. Up until now, I've been doing with end behavior and all of it. That's end behavior over there. Let's talk about now real zeros. How many times does this graph here cross the x-axis? In other words, what I want to know is, where is y equal to 0? Well, it's equal to 0 right here, and right here, and right here. That means my degree is at the most, or at least 3. There's a connection there. How many zeros are on this one? Well, I got 1, and then I got 1 right here, and then 1 right there, and then 1 right there, and so that's then going to be 4. But it doesn't always have to touch the maximum number of times. You could have a graph that's cubic with a cubed exponent, and it might look something like this. Okay. How many real zeros does this graph now have? What I'm asking you is, how many times does it cross the x-axis where y is 0? Well, that's just once. I might have had 2 more in here if it had come down and then gone up, but it didn't. It kind of missed coming back down. So there's only 1 real zero here. An odd degree function will always have an odd degree number of real zeros. It'll have the same number that you see there as an exponent, or it will have 2 less or 4 less or something like this. So for this graph here, it's going to be a cubic. It's somehow related to something x cubed, but it only has 1 place where it crosses the x-axis. Now, the question then becomes, what is that location? Where does the 0 happen? And so from a graph, you can look in there and you're like, oh, well, that's where x is equal to -3 right there. Looks like it. Okay, nice. But what if your graph doesn't cross right at a grid line? Well, then you got to estimate. So let me see if I can get one here that doesn't cross right at a grid line. Let's see if I can do something like this. That'll work. Okay, where are my zeros here? Not what are my zeros. My zeros are 0. Where do they occur? Where is my y value 0? Well, I have one of them, the first one on the left, right here. What is that? Well, here's the origin. So here's -1, -2, -3, -4. This is -4 here, -5. It's somewhere between -4 and -5. Where does it occur? I don't know. Maybe x is equal to about, like, that looks pretty good, like in the half. No, maybe not in the half. X is equal to -4.4. I don't know. It's an estimation. I've got another one right here. And that's between 0 and 1. So maybe this 0 is where x is equal to 1.3 maybe. And then I have another one here at that location, but that also is a little more than 1, 2, 3, 4. That's maybe something like x is equal to 4.2 or something like that. So when you're asked to find zeros, sometimes they lie right on grid lines, the x values where it crosses and makes y is equal to 0. Sometimes not, and you're going to have to estimate that, okay? So that would be zeros. Now, this one over here obviously has 4 at this moment. 1, 2, 3, 4. And that makes it an even degree. And you'll notice with an even degree, the ends both point the same direction. They either both point down or they would both point up. It doesn't always have to cross at exactly 4, even if the degree is 4. We might have something where it does this. Comes up and then a little barbell and then comes down like that again or something like that. And now I've only got 2 here and here. I might have had 2 more here and here if this had come down low enough, but it didn't. Okay, so like what happens to those zeros? Because this is something, something, something 4. I've got 2 real ones. Where are the other 2? Because I'm supposed to have 4 total. Am I supposed to tell you that yet? 2 are imaginary, right? They're kind of hidden right up in here. Alrighty. So anyway, that's where you would need to find zeros from a graph. Now, what about this table over here? How do you find zeros from the table? Remember what a 0 is asking you. It's asking you what is the x value that gives you a y value of 0. Y is equal to 0. You're going to have to go through the table and you're going to have to find out where the sign changes from positive to negative or negative to positive. If I go from a 35 to a negative 2, doesn't there have to be a 0 somewhere in here? Probably closer to negative 2 than 35, right? So what x value gives me a 0? I don't know, something between negative 2 and negative 1. Somewhere in the middle here, I get an x value that gives me a y value of 0. Have to. I have to have a 0 in there if there's no jumping around, if it's a continuous kind of a graph. Okay, look for a sign change in the table. Just like over here, you were maybe looking for going from a positive y value to a negative y value. Well, that guarantees that you've got a 0 in there somewhere, because you can't go from positive to negative continuously without crossing 0. All right, so is there another sign change? Yeah, there's one right here. Okay, there's a 0 in here someplace, probably closer to negative 4 than negative 19. So there's also an x value somewhere between 1 and 2 that gives you a y value of 0. That's how you would look and find it in a table. Okay, this is a key skill. I might have mentioned it before. Reading between data points is called interpolation. It's a very good skill. You should know it. All right, so now we need to talk about one more thing, which is extrema. Extrema would be relative high or low points. So coming back over here to the cubic sort of graph. Oops, I didn't mean to erase the whole thing. I just want to erase that stuff. Now, the graph is going to go forever down at this point on the left and forever up at this point on the right. So where is my ultimate end high spot? It doesn't have one. It kind of goes up. It goes up forever and ever on that one. And this one goes down and down and down forever on that one. But there is an area where I have like a relative high spot. If you notice, the graph comes up and up and up and up, increasing. And then right here, it turns around and goes back down. So this location right here is called a relative maximum. Right there at the very, very top. Okay, it's not an absolute maximum because I probably got some points way over here that are higher. Maximum, what does it mean maximum? I mean the y value. The y value is the highest locally, like just in the area. What do you mean? Well, this y value is like, what is that, 2 right there? It's a little more than 2. hey, this y value is between 1 and 2. Hey, this y value over here is between 1 and 2. Here it's almost 2. Here it's 2, but this is still a little bit. This is the highest y value in kind of the general vicinity, just in the local region. Okay, relative maximum. Now, where it occurs is the x value. So if I'm going to say where it occurs, I would say it occurs when x is approximately, what is that, negative 1.8 or something like that. What is the relative maximum y value? It looks like it's maybe 2.2. So I have a relative maximum at x is equal to negative 1.8, and the relative maximum value is 2.2. Keep in mind, where it is the x thing. What it is the y thing. But I also got something else. I also got a relative minimum right here in red. This is a relative minimum. It is a low point. Now, it's not the... It's not the lowest. Obviously, down over here, I got y values that are lower. But locally, it is the lowest point. So you can think of it this way, like a relative maximum is going to be like a hill, and a relative minimum is going to be like a valley somewhere in there. So where does it occur? Well, this looks like it occurs when x is equal to, what is that, maybe 2.1. It's just a little farther to the right than negative or positive 2. And how low does it go? Well, the low values over there, what is that? That's like a y value of maybe negative 2.2, something like that. So I have a relative minimum now at x is equal to 2.1, and the minimum value is negative 2.2. In other words, it doesn't get any lower here than negative 2.2. After it reaches negative 2.2, it turns around and goes back up again. So being able to spot relative maximums and minimums off of graphs is kind of easy to do. Maybe it's a little harder when you're dealing with a table. Let me kind of clear out some of this clutter here. We'll look for high values and low values regarding a sign. So let me look here first in the negatives. Negative 2, negative 5, negative 4. The minimum is going to occur somewhere around here. Now, I'm not sure exactly where, but negative 2, negative 5, then back up. This is obviously changing direction. I think maybe my minimum is in here somewhere. And then my x value that gives it would be over here. This obviously is the high point. 35 is higher than negative 19. It's a little harder to do in a table because you don't know what it's doing right or left. I may have the high point, I might not have the high point. So if I'm looking just in a table, I might just have to say, hey, the relative minimum is this right here in the table. The minimum value is 5. It happens when x is equal to 0. And the relative maximum is here. 35 is the maximum, and it happens when x is equal to negative 2. Okay. Relative minimums and maximums. Whew, that was an awful lot. I think I'm done. Yeah, I think so. This is just an introduction to polynomials. So what did we talk about? We talked about how to write a polynomial. We talked about the degree of a polynomial and the leading coefficient. We talked about two different kinds of polynomial graphs. An odd degree is going to be one where the ends point in opposite directions. An even one is going to be where the ends point in the same direction, down, right? We talked about the number of zeros that crosses then on an odd function, or an odd degree function would be an odd number. We don't always have to have 3, we might have 1. An even function, though, will have an even number of places, like this one would be 4, and I got 2. Or I guess the possibility could exist, you could have 0. See, you could have an even function that did something like this, came up, did a little barbell, and then went back down, and then never crossed the x-axis. So that could even be 0. And we saw that with parabolas, if you think about it. We had parabolas that did not cross the x-axis. When we solved those equations, didn't we have certain types that had like 2 imaginary zeros that like didn't exist in the real number system? That's what those graphs would look like. And then so then we talked about end behavior and how to find extremas. And yeah, that's pretty good for an introduction. The details of it get really interesting. How many, what kind? There's like Rene Descartes came up with a set of rules for like how many times the sign changes on your polynomial, how many times you got this and that, and it's technical, it's good stuff. It's nice. It's getting a little harder than Algebra 1. You're going to have like 4 or 5 maybe different kind of little things that you're going to have to pay attention to, like the degree, the leading coefficient, the number of times the sign change for a positive x, the number of times the sign change for a negative x. Other things like that, extremas, relative maximums and relative minimums. But you put all those pieces together and you get a very clear picture or understanding of what's going on. It's complicated. But life is complicated, and so mathematics, if you're going to be an engineer, this is good. You need this. If you're not going to be an engineer, this is good. You need this. This is helping you to think and manage a lot of different things that all do fit together in the end, rightly, and it's teaching your mind to manage all of that. And so, why does a weak body bother us, but a weak mind doesn't? And that's my little paraphrase from Blaise Pascal, who's over here on the wall next to me. When we go to the gym, we do difficult things like bench press and, kettlebell push-ups and stuff like that. Why? Well, strength of body is its own reward. You're kind of in the gym right now for your mind. You're developing strength of mind. And you may ask your coach, Coach, when am I ever going to do kettlebell push-ups in my job? Never. Or even in your sport, right? If you're a basketball player, do you do kettlebell push-ups as part of your basketball game? No, but you need the strength, okay? And so, kind of like mathematics, when are you ever going to do end behavior of polynomial functions in your job? Maybe never. That doesn't mean that you don't need the strength of mind that they produce. So don't despise the strength of mind. Work at it. It's not easy. It's hard. And precisely being hard is what makes you strong when you do it. Me too. So anyway, I hope you have a great day, and I will talk to you next time. Bye-bye.